I'm Josh Case.
I'm Gabe Jansen.
I'm Tynoff.
I am Ethan Brewer.
I'm Evan LaViolet.
I'm Nathan Pasalacqua.
And my name is Brennan Galley, and we are part of the Supermileage Systems Enterprise. A little overview on what we're going to talk about. We're going to tell you who we are. We're going to tell you about our competition. We're going to then go into our 7 senior designs, where each person will present their own. We had 1 working on our prototype vehicle and 6 working on our new next generation urban concept vehicle. Basically, as an enterprise, our main goal is to build a highly efficient vehicle. It's an internal combustion engine. It's in the prototype category. And then we go to the Shell Eco Marathon competition. We currently have 38 members. It's made up of 10 majors, 3 sub-teams. We have 25 total projects on the team. And we have 7 senior designs going on this year and carrying into next semester. So Shell Eco Marathon, we go down to the Indianapolis Motor Speedway. We take our car around the track, and then we get read out our total fuel usage. And the goal is to optimize that, get as high of a fuel mileage as possible. Now, there's 2 different categories. There's prototype, where you have 3 wheels. It's mainly for efficiency, a lot less constraints. We're trying to venture over into the urban concept category. That's where you have 4 wheels, parking brake, head and tail lights, things along those lines to make it more complicated and make it more like a realistic car. Now, at this past Shell Eco Marathon competition, we ended up placing 3rd overall with 759 miles per gallon. We even won the Technical Innovation Award for our new electric starter design, which was used to minimize the amount of electrical consumption that our entire vehicle used.
This is the ICE Controls and Tuning Overhaul Senior Design. My project objective was to change a bunch of the sensors to make tuning the engine easier and more efficient. I manufactured a camshaft timing gear and modified the valve cover to make the cam position sensor work with our engine. And I also added a fuel pressure sensor, air intake temperature sensor, and a wheel speed sensor. And I also swapped our coolant temperature sensor and our manifold air pressure sensor. As a result, we were able to achieve 759 miles per gallon and 3rd place at Shell Eco Marathon competition. In conclusion, the cam position sensor helps with the synchronization settings of the engine, and we were able to achieve a peak torque of about 1.4 pound-feet.
All right, this is the Urban Concept Shell Aerodynamic Design Project. This is part of the first wave of Urban Concept Design projects in SSE, which was started in fall 2024. Now, the objective of this project is to design a shell which minimizes aerodynamic drag and weight while still complying with the Shell Eco Marathon rules. Also part of this project is creating a manufacturing plan for the shell. Now, with this being an urban concept car, it's subject to quite a bit more rules and constraints compared to the prototype class. So I've compiled just a short list of rules here to give you an idea of what we work with within the project. Now, moving on to the design of the car, the first thing we did was develop a design space model, which you can see in the top right. And this model essentially compiles all the rules and allows us to better visualize the design, as well as easily check if designs are compliant with the rule set. Now, we use iterative computational fluid dynamics to guide the design of the shell, which is essentially performing a baseline test of the vehicle in CFD, and then performing a small design experiment to the car, so changing something like in the tail, for example, or in the wheel wells, and then running that back through CFD and seeing if that either hurt or helped us. And of course, we're guiding that both quantitatively with things like the drag coefficient of the car, and also qualitatively with things like the pressure distribution over the surface of the car. So our final drag coefficient we achieved this way was 0.1211, which compared to the current world record holders in our category, they have a drag coefficient of 0.1365, so we are beating them by a little bit, at least theoretically. Now for the manufacturing plan for the shell, we've decided on a carbon fiber monocoque design with foam core reinforcements, which you'll hear about more in the internal structures project. Of course, with carbon fiber, you need a mold to manufacture it, so we've considered a few different options there. We ended up settling on a direct negative mold manufacturing via 3D printing, and we've already verified the feasibility of this method with a subscale model of the prototype car, and we've also constructed a subscale model of the mold for the urban concept car as well. Now, future work for this project, aerodynamic validation is one thing that could be done just to verify that that final drag coefficient is actually accurate and correct. We also need to secure sponsorship for manufacturing, obviously creating a whole new carbon fiber car from scratch is going to be quite expensive, and we also need to obviously manufacture the shell.
The objective of the Urban Concept Steering Project is to research and design a steering system that is lightweight and simple to design around. The steering mechanism that our team chose is called Pitman arm steering. This type of steering can often be found in go-karts and semi-trucks. The main benefit of this mechanism is that it is extremely lightweight. In essence, it's a simple 4-bar linkage with a crank in the middle. The next thing our team did was calculate Ackerman's steering angle. Basically, when you turn, you want your inner wheel to turn at a greater angle than the outer wheel. This will make the steering easier and make the car more efficient. The angle for Ackerman's steering was determined to be 40 degrees as shown in the graphs. The stub axle and knuckle can be seen in this slide. The stub axle is made out of aluminum 6061 and the knuckle is made out of a composite sandwich. These are fastened together using M6 bolts. The stub axle forces were calculated using various vehicle dynamic formulas. The situation that the vehicle was undergoing is braking from 25 miles per hour to 0 in 5 seconds. With these forces, the stub axle still survives with a factor of safety of just under 2 and a total deformation of 0.8 millimeters. Future work would be continuing on with the design on the steering column and manufacturing the parts that were designed this year.
This is the Urban Concept Internal Structures Senior Design Project. The project objective of this is to design a vehicle frame, dash, and seating for the Urban Concept vehicle. Some of the other objectives are to minimize weight and maximize strength. A couple of the milestones I'll go over throughout this project were create constraint table, research frame design, create initial frame design and constraint model, research sandwich composites, then choose core material for sandwich construction, manufacture 36 sandwich samples for mechanical testing, test these materials using 4-point bend testing and edgewise and flatwise compression, then compare testing results and iterate on frame design with FEA. Some of the key constraints are listed as well, which are the same as the other Urban Concept vehicle constraints. For testing, I created 36 samples. I tested various core and skin thicknesses, which you'll see on the next slide. And the goal was to find the best strength to weight ratio and take the modulus of elasticity and ultimate strength and bring it into FEA so I could iterate on my design. The results is that the winner in terms of strength to weight ratio was the sandwich with 1/4-inch foam and 2-ply skin thickness on each side for a total thickness of 0.295 inches. This won in strength to density, as you can see in the green highlighted box, with an internal ratio of 402. Future work is to continue iterating on current frame design and complete FEA with the modulus and ultimate strength that I have found in my testing.
So the primary objective of the Urban Concept Electrical Systems Senior Design was to design, manufacture, and test the electrical harnesses for the electric Urban Concept vehicle. Main project goals were to create a simple, low energy consumption electrical system, because obviously that'll count towards our mileage as long as we keep the electrical consumption low. There was 3 main subsystems of the entire electrical system. There was the bulkhead electrical panel, the yoke, and the driver bay. Now, moving on from that, design overview, we're looking to have a 48-volt system. So higher voltage, that is what is allowable by Shell, is a 48-volt system at the max. We're using automotive grade wire, so 18 gauge TXL. We're looking for DTM series connectors because they have an IP67 rating. The wet car has to be able to run in the wet weather. That way we don't have any issues or any shorts with our electrical system. Now here's the electrical schematics for the main electrical panel. So this is the bulk of the electrical system. In the top left, you can see the motor controller actually from a senior design last year. This is what will be driving our powertrain. It's a custom motor controller, which is required by Shell rules. Now for the yoke, we're going to be using the TNC 4.1 with the CAN transceiver. It has one of the highest processing rates, so this is part of the reason why we took it. We're looking to implement a CAN system in the actual vehicle, just like any other vehicle that you'll see on the road today. Now, for future work, we do still need to manufacture these harnesses and then test them, make modifications. This will come when the actual vehicle has been manufactured, so the body. We need to do the OEM windshield wiper system, so the mechanical design behind that, and then the drivetrain testing and optimization. So looking at the electric motor, optimizing the gearing ratios, things along those lines. We're going to work with the software team to integrate the telemetry systems, and then once everything is ready to go, we're going to integrate it into the vehicle.
So this is the Urban Concept Rear Suspension and Subframe Senior Design Project, which was started this spring. And the objective of this project is to design a rear suspension and subframe system for the Urban Concept car that is lightweight and minimizes energy losses due to vibrations and other impacts, while also being strong enough for safe operation and also complying with all of the Shell Eco Marathon rules. For the design of these systems, a dependent trailing arm suspension was found to be the most suitable due to the existing shell and internal structures designs, as well as being both lightweight and less complex. For the suspension aspects of the design, rear mountain bike coilover shocks were selected as they are relatively lightweight, low cost, configurable with different coil spring rates, and also have adjustable damping on them. The rear subframe is designed to be made out of 1 inch by 1 inch aluminum square tubes, welded together, and also use several 1/4 inch aluminum plates with fasteners to mount to the shocks and the bulkhead of the vehicle. An FEA simulation was conducted and underwent the calculated worst-case scenario loading conditions and resulted in a lowest factor of safety of 2, which is within the desired range of 2 to 2.5. For future work on this project, the design will need to be revised, finalized, and also verified to account for other components such as the axles and hubs of the wheels, the brakes, and electric motor and pulley. A manufacturing book will then be created to verify the manufacturability. And once this is completed, the materials can then be ordered and then used to manufacture and assemble the systems, which will then be tested and verified. And once the vehicle is manufactured, the system can then be integrated into it.
This is the Urban Concept Doors Senior Design Project. This project is currently in semester 1 of 2. The project objective is to design and manufacture the hinge for the new Urban Concept car. These hinges are designed to function similarly to butterfly doors. The main difference is that these hinges hinge from the middle of the car instead of the front. This is version 1 of the design. The only thing not shown here is the mounting brackets for the door and the firewall, but as you can see, they're labeled. Due to the skinniness of the door, the hinge must rotate the door 180 degrees, hence the 2-to-1 gear ratio, because when the door is fully open, it will be 90 degrees from the closed position.
We want to give a huge shout out to all our sponsors for their support over the years, and especially this year as we went and got 3rd place at our competition. We look forward to working with them in the future. With that, thank you for watching, and we hope to see you at Design Expo.